We briefly talk about sequences. I'm actually going to skip over infinite series. I don't think we have time. You covered them somewhat in Calc 2. So I hope you know it. They're in my notes. You should definitely have it in the notes, everything in my notes, possibly on the exam. So just maybe 30 pages of my notes here. But I'll cover the new ideas. So sequences, real valued sequences. In R. Some we can just in general say sequences in Rk in some Euclidean space. So recall the definition. So a sequence xn, which is part of Rk, is a function f from the natural numbers into Rk. Right? So a sequence is really just a function of the natural numbers into the particular space. We did it for a general metric space. So we had also other conditions. We said we say that that sequence is bounded Oh, we missed you, Bart.
How you doing?
How are you? Sequence is bounded if what? If there is a ball of radius r centered at some x that contains the entire sequence xn. Okay? So another way of saying this is equivalent to the range of the sequence, to saying that xn, where n is bigger than or equal to 1, has finite diameter. You recall what diameter is. So diameter of the set xn, n greater or equal to 1, is just the supremum of all possible distances from points in the sequence. So that's simply equal to supremum over any n m of the magnitude xn minus xm. So that's the supremum for sequences. Supremum for, in general, for any set A, you just take the maximal distance or the supremum of the distances between any 2 points in the set. So that's, I guess, still something we learned. So in other words, the sequence is bounded if the range is bounded, or the diameter of all the possible distances between any 2 points of the sequence. In this case, let's say this is norm 2. But you can use any norm, in fact. If it's going to be bounded in one norm, it's going to be bounded in the other norm, since all norms on Rk are equivalent. I haven't proved that, but we know that the 2 norm, the 1 norm, the infinity norm, we didn't mention others, they're all equivalent on any finite. But there is going to be, maybe after compactness, I'm not sure if we'll cover it in this course, but when you know what compact sets are, you can prove that any norm on a finite dimensional vector space is equivalent to any other norm. So that gives you a great flexibility on the distances that you use in Calc 3. So if you read advanced books on Calc 3, let's say if you read Mancri's analysis on manifolds, he uses the supremum, the sup distance usually. But sometimes you might prefer the one distance or the two distance. You can just pretty much switch between them without any repercussions. So we also make statements like the range of a sequence is infinite if the cardinality of the set Xn is bigger than or equal to the cardinality of the natural numbers, finite otherwise. I think you know what I'm saying. So, very basic examples. So, example A, if I take xn to be equal to 1 over n, our favorite sequence, then we know that the limit as n goes to infinity of xn, and when I say limit, I'm using the default distance on the default space, that would be 0. Right? So when you do it in calculus, you assume that you are dealing with real numbers and that you use the usual metric on the real numbers. Range is infinite. And the sequence is bounded. You agree? So if I take example B, I can say xn equal to, let's say, n squared. So sequence is unbounded. Divergent and has infinite range. So, example C, if I'm using xn to equal to, let's say, the number I to the power of n. We haven't really talked about complex numbers, but I to the power of n, it's really, if k is equal to 2, on a two-dimensional space, you can define a field, which you call the complex field. So what is this? This is root of minus 1. So to the first power, it's root of minus 1. To the second power, it's minus 1. To the third power, it's minus I, etc. Right? To the fourth power, it is 1. So then we say that that the sequence has finite range. Why does it have a finite range? Well, let's look at it. X sub n can equal, so equal what? It equals to I minus 1 minus I or 1. Those are the possibilities, depending on the n, right? So only finitely many points are actually repeatedly hit. Finite range, sequence is divergent, and bounded. Well, so let's look at D. If I take x sub n equal to 1 plus minus 1 to the power of n divided by n. So what can we say? We see that xn under the usual metric goes to 1. Obviously, if it's Cauchy, it's bounded. We already talked about it. Xn is bounded and has infinite range. Yes? And we have the following theorem regarding sequences. I might prove one result and move on. So suppose that we have a sequence xn and yn in Rk. We have that xn goes to x, yn goes to y. And if this is the case, then you have by limit laws, which you established by delta epsilon, you have that limit as n goes to infinity of xn plus yn is simply x plus y. You also have that limit as n goes to infinity of some constant times xn will be c times x. And that's for any number c. So by number I just mean, in our case, in R. So that's B. Then property C is that if I take the dot product of x, n, and yn, so limit as n goes to infinity of the dot product xn with yn, that dot product will give me x dot product y. And then D, if k equals to 1, I can take 1 over xn. 1 over xn will go to 1 over x, provided let's say that xn are not 0 eventually, and x is not 0. Okay? So, in other words, this is a general k-dimensional space. If k is equal to 1, it's just a real space, and we have this result. Okay? So I will not prove A. Let's say maybe I'll prove C, and if you want to, we'll do D. Okay? Proof. A through B simple. So let's do C. So the dot product is a real number, correct? So what you do is you consider the difference of xn dot yn minus x dot y, and you can write this as xn dot yn minus xn dot y plus xn dot y. You see I inserted the term minus x dot y. So I hope you reviewed dot products from Calc 3. I have even videos on that if you tried. So this is less than or equal. I can break the this is absolute value. So the absolute value of a sum is less than or equal to the sum of the absolute values. So this is less than or equal to xn dot yn minus xn dot y plus xn dot y minus x dot y. Now, if you know how dot product behaves, quite like a product, it is multiplicative. Sorry, I can factor out xn out. So this is the same as absolute value of xn dot product yn minus y. Good. Plus, this is the same as xn minus x dot product y. So, what can we do? Here is a dot product. We recall Cauchy-Schwarz. So by Cauchy-Schwarz inequality, this is less than or equal to the norm of xn times the norm of yn minus y. Plus the norm of xn minus x times the norm of y. That's Cauchy-Schwarz. Correct? So now this is going to go to 0 by hypothesis. So this can be made less than epsilon as soon as I delete enough terms of the sequence. That's the idea, right? Delete enough terms of the sequence. Little n is bigger than capital N. This is very small. Then I'm a little bothered by the xn because this changes. Right? This y is just a finite number in norm, so it's not bad. This goes to 0 times a finite number, not bad. So you can do the following. You can either use a theorem to say that if xn is convergent, it's Cauchy and all Cauchy sequences are bounded, and you can say less than or equal to a bigger bound. Or you can do the following. You can then, if you don't want to use that result, you can say this is equal to xn minus x plus x times yn minus y plus xn minus x times y. And I can use the triangle inequality again. In this case, I use triangle inequality on the 2 norm, which we already learned. So what is this? This is the same as the product of xn minus x times yn minus y plus x times yn minus y plus xn minus x times y, and this entire thing goes to 0 by, well, this thing goes to 0. I should say just pick large enough, just as soon as you pick a large enough n. I'm not going to write it. I'll just say this goes to 0 How do you do that rigorously? Think about it, right? So this product, as soon as n is big enough, this is less than epsilon, this is less than epsilon, so less than epsilon squared. You can already say epsilon is smaller than 1, so epsilon squared is smaller than epsilon. This thing is less than some quantity x times epsilon, some quantity y times epsilon. So you see that this is, you might say that this is less than or equal to some constant b times epsilon. And basically, you can loosen up the delta epsilon definition. So as soon as you know that something is less than b times epsilon, that's already the same as proving that it's less than epsilon. Because you can then take epsilon divided by b. Right? So that implies that we have convergence to this thing goes to 0. Yes? So sorry if it was no, I just got lazy at the end, right? You understood that you can do a rigorous delta epsilon, it's not a big deal. And maybe I'll mention a little bit about D. Again, not anything difficult yet. D, what do we have? We can say that if I look at 1 over xn and I subtract 1 over x, that's the same as x minus xn divided by x times xn. Okay? And I can show that this goes to 0. So if I take the absolute value here, take the absolute value here, this is equal to xn minus x divided by absolute value x times absolute value xn. And since the sequence xn goes to x, and we assumed x is not 0, so there is a lower bound. So this thing is less than or equal to some constant b times xn minus x, which goes to 0. And why? Because how do you create the constant b? So b, so we just if n is large enough, such that the absolute value of xn minus x is less than, so if it's large enough, x is a non-negative number, so this one is going to be less than, let's say, absolute value of x divided by 2. So when I open it up, it means that xn minus x is less than absolute value of x over 2. and bigger than absolute value of x divided by 2. Correct? This number is positive. Eventually, if n is large, they converge. Basically, we have convergence to x, so we have this situation. So what I'm drawing is this situation. So somewhere over here is 0. Absolute value of x, I might as well assume that x is positive. So x is located somewhere in here. And the terms of the sequence xn are eventually all gathered away from 0. They are eventually only here. Pxn. Yes?
In the second line, it says absolute value of x over 2. Should that be negative?
Yes. That's negative. Very good. So what you have is, what you then have is that if you move the x across, so you have that this is x minus absolute value of x over 2 less than xn, and that's less than x plus absolute value of x over 2. So if I basically made the assumption that x is positive, right? Without also generality, x is positive. Otherwise, I multiply by negative. Right? So what we have is that xn is the absolute value of xn is bigger than absolute value of x over absolute value of x over 2, which implies that 2 over x is bigger than 1 over xn. So we have this as the bind. So that gives us a way to create our b, because b is just what is b? B is 1 over xn. B is 1 over absolute value of xn times 1 over x. So B is, so we have 1 over xn times 1 over x, and this is smaller than 2 over absolute value of x times 1 over x, and I can take this to be my b. Yes?
Since we're given that that xn converges to x, why can't we just say for a large x,
You can.
for a large n, 1 over x equals 1 over x, and then just say 1 over x minus 1 over x?
They're not equal. You don't know that they're equal, but basically what I did is kind of in this picture. What you can say is that the distance between xn and x is the distance between xn and 0 is large. So that allows you to create an upper bound. In essence, what I'm saying is that 1 over xn is bounded. Really, you might ignore all this entire statement and just conclude that 1 over xn converges, therefore 1 over xn is bounded. Instead of doing those inequalities, maybe you can just do the following. 1 over xn is, sorry, I don't know that 1 over xn is conversion. My fault. Otherwise it would be right away. But 1 over xn is going to be, if all the xn are away from 0, then 1 over xn is bounded, correct? They're all bounded because basically the only way to get large values is to go to infinity. The largest we can get is, in this case, the thread boundary. 1 over the thread boundary is the largest, is a supremum of the Xn. So really, this is what I need to tell you. The important thing is upper and lower limits. That's the main topic. So what you have is given a sequence an that belongs to R, the sequence can be very badly behaved. Be behaving badly. In other words, it's all over the place. So for example, if I take a Q as, if I list Q in a sequence, then it jumps all over the place, okay? But the problem here is, could we create an upper sequence and a lower sequence to a sub n that behave in a monotonic fashion? Sequence, let's call this upper sequence capital P sub n, and lower sequence Tn that are monotonic or monotone. So in other words, the sequences are either increasing or decreasing, rather than just jumping all over the place. Okay?
So the goal is to so you're rearranging the set?
No, not quite. The goal is like in squeeze theorem. Could I squeeze the badly behaved sequence between one upper sequence that falls down and one lower sequence that rises up? And we're going to try to understand how we do it. Okay, so the idea is that we want the Tn to be decreasing right? That's one condition that we want. Second condition that we want is for the little Tn to be increasing. That should be plus 1, sorry, right? So it's decreasing. The little Tn are increasing. And the third condition is that if I look at An, it's wedged on the top by capital Tn and on the bottom by little tn. You understand? So what we attempt to do is some general procedure to implement a squeeze theorem. Right? It's not always going to be possible, obviously, to squeeze the sequence because the sequence might not converge. But could we create the best possible scenario? So those Tn and little tn and capital Tn are like the best possible upper and lower bound for the particular sequence. Like the best possible squeeze theorem. Right, remember, if you recall calculus, there might have been several results that you proved using the squeeze theorem, and it's usually rather hard to come up with the upper function and the lower function to create the squeeze. So here for sequences we study some sort of optimization. could we create the best possible upper sequence and the best possible lower sequence that will be implemented in the squeeze theorem. We will see very soon when we talk about continuity that all issues of continuity on the real number line, or for that matter in Euclidean finite dimensional space, can be resolved in terms of sequences. In metric spaces, that's also true, right? In any metric space, you can resolve many questions by just studying sequences. So this will help us study the sequences in R, and other spaces are generated from R. So how do we proceed? We are in R, so we know something about those sequences. So what we're going to do is we're going to define capital Tn to be the supremum starting from n. So the supremum, I'll write it like this, supremum where k is bigger than or equal to n of a sub k, which is really the supremum of a sub n, then a sub n plus 1, then a sub n plus 2, and onwards. So the supremum, at least in the expanded real number line, it's either equal to infinity or it's a bounded number. Right? So the sequence is either bounded above, and if not, the upper bound will be infinity. So that's the supremum of the sequence, and we define little tn to be the infimum of the same sequence. Good? So then, using those results, let's verify what's happening, right? So clearly we have condition 1. 1 is true as written over there. Do you see why? Let's try to see why 1 is true. So let's consider T1. T1 contains, T1 is the supremum of the full sequence. So that's the supremum of A1, A2, A3 onwards. Right? What can you say about the relationship between T1 and T2? All right, T2 here. That would be supremum where k starts with 2. So I deleted the first term of the sequence. What can you say about the relationship of T1 and T2 and why? So what happens, right? I had this set containing a sequence A1, A2, A3, and now I have a set containing one element fewer.
It must be less than or equal to 2.
Less than or equal. Exactly. Why? Because either I deleted the maximal element. If I deleted, you see, either the set contains already a maximum point, and I deleted it, and then the supremum declines, or I haven't deleted the maximum element, and therefore I haven't changed the ceiling. I deleted some part of the sequence. There are plenty of others to hold the ceiling on, right? You have this visualized? Easy, right? You see that the ceiling is held by the sequence, unless the pillar was A1. If you remove the A1, the ceiling falls a little. Yes? So, and then in general, you can see that you would have that Tn is bigger than or equal to Tn plus 1, because deleting a point after Tn, I either drop the ceiling more, or I don't change the ceiling. So at each step, I either delete some element that is the maximum for the sequence, or I don't delete anything that maintains the ceiling and it still holds.
When you say bigger, do you mean size?
It's a number. You read that supremum. It's so if I have a sequence, I can take the sequence and I can write it on a vertical number line. That's how I visualize it, right? So I have the a ends. They are spread on the vertical number line. And then what I do is I drop the ceiling until basically until the ceiling falls onto the AN, or so to speak, if it falls lower, the AN are above it, right? So that's the least upper bound, remember it, right? So the sequence might not have a maximum, but if it's a real valued sequence, it always has the least upper bound. That's how real numbers are constructed. Good? So the T's, the capital T's, are either it's infinity, either T1 is infinity, in which case T2 will be infinity since they're also real numbers, right? Infinity means, well, no number that I remove is maximum, right? And then it just stays to be infinity forever. Or T1 is a real number, and therefore T2 is going to be a smaller real number, T3 is going to be an even smaller real number, etc. Good? We're going to give some examples in a moment, so you see how that works. But T1 is bigger than or equal to Tn plus 1. That holds. Similarly, 2 also holds. I don't want to write it out. Why is the infimum sequence decreasing? So just like you have supremums, you have infimum, which talks about the floor. So either you remove a minimal element, in which case the floor goes up, or you haven't removed the minimal element and the floor stays where it is. You understand? The only way it goes up is if you remove a minimal element. Do you see that? Right? If there is no minimum, in other words, if there are sequences going lower, 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 right? So the infimum, it could be that the sequence goes all the way to minus infinity, and then the infimum will stay at minus infinity. Or the sequence is bounded below, in which case the infimum is of the entire sequence is some real number. Now this real number is either basically a minimum of the sequence, there is a point that actually holds it, in which case when you remove it, the ceiling goes up, or there are always many elements that kind of not quite at this point, but are about to reach it. Okay? So, and of course, the third condition is also obvious. 3, we have that T sub n less than or equal to an less than or equal to capital Tn. That's also true. Why? Because look at it. Look at the nth term. The infimum already contains an, right? So the infimum is, I'm taking the smallest in a way of all those points. Infimum is very similar to a minimum. You remember that, right? The only difference is that none of those points might actually be the minimum. That's the only difference. So what you do is intuitively you take the minimum of all those numbers, which is clearly less than or equal to the number you have here. And here you take the maximum of all those numbers, which is clearly either this number or something bigger. Right? Supremum is roughly speaking a maximum. It's just that if you have infinitely many points, the maximum might not be there. Right? You all know, you don't have to explain infimum, supremum. That's very good in your head. Wonderful. So now let's see what can we do using those sequences, little tn and upper tn. So since tn is increasing, limit as n goes to infinity of little tn equals to limit of tn always exists in the closure of R, in R bar, which is basically if I allow minus infinity and infinity to be numbers, right? So Tn, what can it do? It grows up. It either grows to its supremum, right? It either converges to its supremum, which is a real number, or it converges to its supremum, which is infinity. So the limit of Tn's, it's going to be, or it will always exist. You remember that monotone sequences always converge. Why? Because if it's a sequence of real numbers that it's increasing, so it increases until it reaches the supremum, or increases to infinity, and you can say that's the supremum. There is no other possibility. Of course, if the t sub n's, they might be at minus infinity. So they either stay flat at minus infinity and never go anywhere, so it's a constant sequence of minus infinity, or it's a sequence that grows to a number, or it's a sequence that grows to infinity. So monotone sequences always converge in R. And the limit as n goes to infinity of capital Tn also always. So I should say maybe like this, since capital Tn is decreasing, limit as n goes to infinity of capital Tn always exists. In the closure of R. So let's look at examples. Oh, yes, I should mention what are those things called, right? So you will say something like this. You would say, given the definition, given a sequence an in R, we define limit supremum of an, limit supremum of an. If you want to, you can write n goes to infinity, that's not necessary. And that's the same as lim as n goes to infinity, and you can write the bar on top of limit. And what is this? This is simply limit as n goes to infinity of capital Tn. So what you do is, if you remember, you imitate the squeeze theorem. In the squeeze theorem, you have an upper function and a lower function, and they ended up converging to the same point. What do you do here? You created an upper function, in some sense the best possible upper function for all the sequences, for all the terms of the sequences, and the best possible lower function. And what you do, this limit supremum is checking where the upper function converges to. And limit infimum will check where the lower function will converge to. So you get it, limit supremum is just the limit of the supremums. It's basically what I do. I create a sequence of supremums and I delete terms of the sequence one by one. So I have supremum of the full sequence, then supremum of the sequence starting at 2, then supremum of the sequence starting at 3. And what we have is we have a decreasing sequence. And I check where does it go to. And I also define limit infimum to be, this is one notation for it. And really all that is the limit of the t sub n, little t sub n. Okay? Well, let's try to do a few calculations and see what the calculations imply.
So what is
Yes?
that line under the limit?
That's like lower limit. It says the floor. So instead of writing limit infimum, you might write limit with a floor sign or limit with a ceiling sign.
Oh, I didn't see that.
Right. Right. So let's look at examples. Again, it's very tiresome, but let's try to do it with 1 over n. Could you please tell me what is capital T sub n? Capital T sub n. So the sequence is 1 over n. Maybe, so it's not so scary, let's do it with capital T1. What's capital T sub 1? Sequence is 1, 1/2, 1/3. What's capital T sub 1, please? 1. What's capital T sub 2? 1/2, right? Because you dropped the 1, and 1 was the supporting pillar for the ceiling. So that's 1/2. And in general, what's T sub n? Capital T sub n is, this would be 1 over n. Ends up being the same as the term of the sequence. Okay? And now let's try to see if you can right away tell me what is little t sub n. Little t sub n is 0. What you do is you take the full sequence, take the infimum, you see that the sequence goes all the way to 0. You remove 1, still the sequence goes to 0. You remove 2, still it goes to 0. So the little tn is constant, it just stays 0. And the upper ceiling is collapsing. Okay? So then what you can see is that, again, this is trivial, but an is less than t sub n, which is 1 over n, and bigger than little tn, which is 0. Okay? So we have a squeeze. So this guy, as I push to 0, goes to 0. This guy, as I push to 0, goes to 0, forcing this guy to go to 0 because they go to the same place. Right? So there's a very trivial squeeze theorem here. Good?
Professor, I remember something with the squeeze theorem where the function itself can't be the upper bound or something.
Well, it really, with the squeeze theorem, you're trying to resolve the limit of this function, right? But if you know the limit of this function, that's how you knew it's 0, right? There is nothing really to resolve. So for 1 over n, this procedure naturally is useless. Right? A is an example that's we don't really need it. It's just to illustrate what's capital Tn and what's lowercase t sub n. But I'll show you other examples where it might be a little bit more useful. Okay? B. So I'm going to write the sequence A sub n. So this sequence is, I'm going to list it out, okay? I'm a bit lazy to write the full formula. Sometimes I will in the exam and sometimes I won't. So this is 1, followed by 1/2, then followed by 1/2, then followed by 2/3, then followed by 1/3, then followed by 3/4, then followed by 1/4, and etc. If you don't see, so if you don't see what the sequence is doing, just to be sure, A sub 2, okay, the even terms of the sequence are 1/2, 2/3, 3/4. So what is this? This is simply k minus 1 over k. You see this, right? So what do I have here? Even term, if this is k, first even term is 2, this is 2 minus 1. Next even term, the next term will be, if next term is 4, so k is equal to 2. no, you get my point. So it's 2 to the third, right? So this is a sub 2k, and a sub 2k minus 1. It's simply 1 over k. Right? So what I'm asking now is, can you tell me what is capital T sub n? In fact, even without bothering here, let's just even right away calculate the limit as n goes to infinity of capital T sub n. In other words, let's calculate limit supremum of the sequence. What is that? 1. Could you tell me something about T sub n? T sub n, is it decreasing or staying the same at the same number? T sub n, what is it always equal to? Look at the sequence, what does it always equal to? It's always a 1. You see, there is no maximum element, right? You delete something, there is always like 3/4, then there will be 4/5, there will be always numbers that are trying to support the ceiling. So the ceiling actually never falls, it stays at 1. And what can you say about limit as n goes to infinity of little tn? That would be 0. And you see that they are different. Capital Tn and little tn are not the same. In the squeeze theorem, that would not be enough to show that the limit doesn't exist, but here it quite is. It tells you that limit doesn't exist. So if somehow you could calculate t sub n its limit, and you can calculate limit of the lower, the infimum limit, and they are not the same, the sequence cannot converge. How do you know it cannot converge? Because you see that as you delete terms, the ceiling, it falls only up to here, and the floor rises only up to here. So that means that no matter how much you delete, the sequence bounces between those bounds. You see? The limit infimum and limit supremum tells you, as you push to infinity, what's the most compact region in which the sequence is going to be bouncing. Right? Because you see, as you take limit supremum, you are dropping the ceiling. Right? And as you take limit infimum, you are raising the floor. So here you raise the floor as much as possible, here you lower the ceiling as much as possible, and the sequence is not squeezing. It's like gas particles bouncing back and forth. Okay, so that's the point. So we will make a few more examples. We'll give a few more examples, and then we'll write the conclusion. So now let's say that the sequence an is this sequence. 1 minus 1, 2 minus 2, 3 minus 3, etc. What can you tell me about limit as n goes to infinity of the supremum of an? By the way, you see, this you don't have to write n goes to infinity. It's clear what lim sup is. So you can just write lim sup an. You don't need to write n goes to infinity. That's already clear. What is that? What's the upper limit?
Infinity?
Infinity. Are the upper limits, what are they? Do they ever decrease? Capital T sub n, do they ever decrease? Do you see that the answer is not? Because no matter what points you delete, there are plenty of very large points that support infinity as your ceiling. So this is infinity. What is limit infimum of a sub n? Negative infinity. So in this case, lower bound and upper bound never move, because again, those gas particles are very energetic. They are kind of bouncing higher and lower, higher and lower, higher and lower. So they maintain the ceiling and the floor very far as possible from one another. So in some sense, that gives you a measure of how close to convergent is your sequence, right? So the closer the ceiling and the floor to one another, the closer the sequence is to convergence. So when is it going to be used? Again, mostly it's used theoretically. You can define the Riemann integral in terms of limit supremum and limit infimum. Remember when you did integration, what did you create? You created a sequence of approximating rectangles. Okay? The limit supremum would be the best, basically the biggest possible rectangles you can erect. So the sequence of the biggest rectangles you can erect. And limit infimum would be the smallest rectangles that you can erect. And if limit infimum and limit supremum converge, then you have that the function is Riemann integrable. Okay? So that's one major application of what you see here. So D. So we have that A sub n is -1 to the power of n divided by 1 plus 1 over n. So please tell me what's limit infimum of the sequence an. What is that?
-2.
So, yes, no, sorry, no. Negative what? You see, I give you very simple sequences, so it's really, right? So, for the sequence, limit infimum, what do you do, right? You delete a lot of points. When you delete a lot of points, this number is very small. And you see we have negative numbers. We always have negative numbers. So what's the limit infimum?
-1.
-1. You see, just push 1 over n. So you see the infimum is really the same as taking the limit when the numbers are negative, right? It ends up being the same as simply limit where n goes to infinity of -1 over 1 plus 1 over n, which is -1. And what's limit supremum? That is same as limit where n goes to infinity of 1 over 1 plus 1 over n. And that's 1. So you see what happens here. So it means that a bunch of particles or terms of the sequence are gathering near -1 and a bunch of others are gathering near 1. So -1 to 1 is like a measure of how close is it to convergence. So notice an converges if and only if lim sup an equals to lim inf an, and the limit is a real number. I mean, you can say converges to infinity other than that, or to minus infinity, but if you make the statement that this is a real number, this is convergence in your ordinary sense. Right? You see, usually in calculus you said diverges to infinity or diverges to minus infinity. You could also say converging to that if you add those as endpoints.
Professor, but aren't there those functions that seemingly converge but not really, but aren't fast enough to converge? Or is this a new definition of convergence?
Well, what do you mean seemingly converge but not really? What do you mean by speed of convergence?
I remember in calculus there were some functions that appeared convergent because they approached a certain point, but they weren't like 2 over n or something.
You're talking about harmonic sequences. or harmonic series. So the sequence converges to 0, but the sum does not converge, or the sum converges to infinity. That's what you're talking about. Which means you should read the notes in chapter 3 that I wrote, right? So there are series that I'm unfortunately skipping. I'm happy to talk about it after class. So those things are discussed somewhat in my notes. But that's a review of Calc 2, but not using integration since we haven't covered integration. So you have a comparison test, but it's not using, or something similar to the integral test, but not using the integral. So an converges if and only if supremum, limit supremum, and lim sup and lim inf are the same terms, right? So one direction is obvious. So because if you have so I want you to see that both directions are quite clear. So first of all, if Tn goes to some value t, which is equal to little t, which is what little tn goes to. Okay. So if this happens, then what do we know? We have that a sub n less than or equal to t sub n bigger than or equal to little t sub n. Those are monotone sequences, correct? So they always go to the same value. So they always have a value to which they go. So this goes to t, this goes to capital T, and since they are equal, since this is equal to t, this guy is forced between capital T and t. Where could it go? It goes to the same value. In other words, that if this happens, then we know that limit of an as n goes to infinity is also limit supremum of an, which is also limit infimum of an. Good? Do you see this diagram, right? It's, you can do it by delta epsilon if you need to, but it's pretty obvious, right? Where could it go? It's bounded. It's the an. Once you delete them, they are bounded between this, between numbers that are close, between those tn and those little tn. So they have less and less place to go, right? The ceiling and the floor merge. There is nowhere to go. You go to where they merge. That's the squeeze theorem. So on the other hand, if the sequence an converges to a, suppose I know sequence converges. What does it make? What does it do with capital Tn and little tn? So what does it imply? It implies that if n is bigger than some capital N of epsilon, remember that's a function, right? Then we know that a sub n minus a is less than epsilon, because an converges to a. And that's the same as saying that an is less than a plus epsilon and bigger than a minus epsilon. Okay? For all little n bigger than or equal to this capital N, this first integer when that happens. Okay? So what happens then? That implies that on the one hand a sub n is less than or equal to capital T sub n, which is less than a plus epsilon, and on the other hand bigger than or equal to little tn, which is bigger than a minus epsilon. Do you see this? So what am I saying here? So look at it. I'm saying that an, all of them, right? So an plus 1, an plus 2, all of them are between those numbers. So then this is a lower bound, and this is an upper bound. So the least upper bound is smaller or equal to this number. I should say it could possibly be equal. This could be equal, but that doesn't matter since I change epsilon smaller, so they will actually not be equal. see? This is an upper bound, so capital Tn is the least upper bound, it must be less than or equal. This is a lower bound, little tn is a lower bound, so it must be greater than or equal. It's the greatest lower bound. So you have this thing. So now what you have is you have by epsilon you have a squeeze. Those numbers converge, and where can they converge? They converge to a number between a minus epsilon and a plus epsilon. Since epsilon is arbitrary, they converge to a number a, nowhere else. Do you see this? So that implies that Tn goes to A, and capital Tn also goes to A. Good? Okay, so that's all I cover. Next class is continuity. I'm going to jump over, I think, I'm jumping over almost 20 pages, and those are infinite sequences in series in R, similar to what you covered in Calc 2. Make sure to read those notes.